This is a workthrough of problem 2 on exam 2 in module 1, which is on page 24 in the book, Problem Solving Guide for Electromagnetism and Optics, 3rd edition. Problem 2 is, there is a plus 7 nanocoulomb point charge, a distance of 10 centimeters away from a minus 4 nanocoulomb point charge as shown in the figure. Give the location of the point in the plane where the electric field is 0. That's part A. Part B, what is the electric field? 5 centimeters directly above the minus 4 nanocoulomb charge, which is right about here. So let's start with a good diagram. We inherited one from the problem. I don't like it. I like to make my own diagrams. I like this better. Have a big dark charge to indicate positive. A hollow charge indicates negative. It's smaller magnitude. I made it smaller. They're 10 centimeters apart. I labeled that in the diagram. Now we have to consider part A. Where is the field 0? If we look in between the two charges, the plus 7 is making a field to the right away. The minus 4 is making a field to the right toward it. The fields add between the two charges. They're never going to cancel each other out. Over here, the plus 7 is producing a field away from it to the left. The minus 4 is producing a field toward it to the right. But in this tug of war, the 7 is always going to win because it's bigger and it's closer. The only way that fields can cancel out is if the point is over here. There is some point over here to the right of the minus 4, which the field's 0. How do we find it? Well, we can start by defining some distance to it. We don't know what that distance is, but we can call it x. And we can put it on the figure. Here's our distance. We're going to call the field 0 right there. Some unknown distance. We can put it into our equations and then solve for that distance. We know the electric field away, r away from a point charge q is kq over r squared. So we can write an expression for the field here due to that charge. The minus 4 nanocoulomb charge produces a field towards it of this magnitude. There's the K, there's the Q, converted to nanocoulombs, divided by the distance between them, which is x, squared. Now let's consider the field produced by this charge at this point. How far is it away? Well, it's 10 centimeters further than x. So it's x plus 10 away. So our expression is K, there's the Q, it's 7 nanocoulombs. And the distance is x plus 10 centimeters. So now we have an expression for the magnitude of the charge of the field produced by this charge and the field produced by this charge at this point, and we know they're in opposite directions. We can put them on the diagram. There's the field from the minus 4, and there's the field from the plus 7. And at some point, these magnitudes are going to be the same. And if we set them equal, we can solve for x. There's the field from the 4, which is x away. There's the field from the 7, which is x plus 10 away. We're going to solve for x using algebra, and we're going to simplify by canceling the k's, canceling the nanocoulombs. So we now have this, which looks pretty good, much simpler. Let's cross multiply. And now let's take the square root of both sides so we don't get a quadratic. This side is the 2 times the quantity x plus 10. The other side is the square root of 7 times x. I can distribute the 2 in the parentheses. I can subtract 2x from both sides. I can factor out the x and divide by the square root of 7 minus 2. And I get the distance is 30.97 centimeters. So the field is 0, 30.97 centimeters away from the minus 4 nanocoulomb charge. 30.97 centimeters to the right of the minus 4 nanocoulomb charge. Let's check. Let's make sure we're right. Let's get the fields. Here's our x, 30.97 centimeters. There's where we calculated the field was 0. Here's the field from the minus 4. It's 30.97 centimeters away. I get 374.9 newtons per coulomb to the left. Now I can calculate the field from the 7, and that is 40.97 centimeters away, which is 0.4097 meters. And I get that the field from the 7, 40.97 centimeters away, is indeed 374.9, and that is to the right. So these two vectors indeed cancel out, and the electric field is 0 at this point. Now I'm happy. We can go on to part B. So we'll start with the original diagram. Now we want the field 5 centimeters above minus 4 nanocoulomb charge, which is about there. The question is, what's the field right here? We can start by drawing the vectors in by sketching them in. The minus 4 is going to make a strong field down. It's pretty close. This guy is 7. He's got a bigger charge, but he's significantly farther away, and the r is squared, so he's not going to have that big of a magnitude, and he's going to be away. His field is away from, like that. So now I have these two magnitudes, these two vectors. I can calculate their magnitudes, but I need to know the distances. I have to get how far away the charges are from the point at which we want to calculate the field. This one's easy. It's 5 centimeters away. That's given. We have to get the distance from the 7 nanocoulomb charge to the point 5 centimeters above the minus 4 nanocoulomb charge. It's 10 centimeters over, 5 centimeters up. That is the Pythagorean theorem. And we get that the distance from the 7 nanocoulomb charge to this point is 11.18 centimeters. With the distances, we can calculate the magnitudes. kq over r squared. The 4 nanocoulomb is 5 centimeters away. The length of this vector is 14,380 newtons per coulomb. The 7 nanocoulomb charge is 11.18 centimeters away. It produces a field of magnitude 5,030 newtons per coulomb. If we're going to sum these up, we need to know the direction of this vector. For that, we can use trigonometry. So let's draw that line, define this angle. The tangent of this angle is 5 centimeters divided by 10 centimeters, which is 1/2. The arctangent of 1/2 is 26.57 degrees. That's 26.57 degrees, as is this angle from the horizontal. So now we can get the components. The x component is 50/30 times cosine 26.57, which is 4,500. The y component is 50/30 sine 26.57, which is 2250 newtons per coulomb, directly up. So now we only have the vertical and horizontal components of the two vectors. We started with that, and then we got this. We took that 50/30 and we divided it into x and y. Now it's easy to get the total x component. That's obviously 4,500. There's the only one. For the y component, we have 14,380 down and 2250 up. Subtracting the 2250, we get 12,130, and it's down. So now we have this. And once we have this, we're almost done, because all we have to do is get the magnitude and the direction. We know the x component, we know the y component of the electric field. There's where we start. We use the Pythagorean theorem with the electric field vectors. 4,500 newtons per coulomb in the x, 12,130 down in the y, and the answer is the magnitude is 12,940. We have to get the angle because we need the direction. So this is the opposite side, 12,130 over here. And we have 4,500 as the adjacent side. It's 69.9 degrees below the horizontal. The answer is the electric field vector at the point 5 centimeters directly above the minus 4 nanocoulomb charge is 12,900 newtons per coulomb, 69.6 degrees below the positive x-axis. So let's put this vector on our original diagram. We started with this. We want to know the field here, and it's down that way, just as we thought. The magnitude is 12,900 newtons per coulomb, and the direction is 69.6 degrees below the positive x-axis. That's the answer to problem number 2 on exam 2 in module 1.